Alright, getting back on our shovel motor here. So we're going to work on the flywheels now. So these need to get balanced, find out what's going on with them. So right off the bat you see a bunch of holes in here. You know it's been rebalanced more than once. Stock holes are on the inside of the flywheel. So these are probably from S&S, came with these holes. And then over here, someone's been dicking with it. So I don't know if it's two guys did it or one guy didn't know what the hell they were doing. Probably both. So this guy here took a lot of weight out of the bottom. This guy took a lot of weight out of the top. These holes here are canceled out by these holes up here. So if you take all these holes and fill them all back up, it's probably going to be pretty close. But I don't know what's going on there. They didn't know what the hell they were doing, obviously. And then you never drill a hole near the crank pin hole because it can crack right through here when you tighten the piss out of this and split. Now with S&S forged flywheels are pretty strong, so it's not really an issue, but if you use more of a stock flywheel, they can break through there, especially if you use 30s and early 40s style Harley flywheels. They were more cast material. They're pretty crappy. I've actually seen those break, especially the 30s stuff. So this here is unknown what it is. Like I said, this here probably been alright if I just left that. Okay, the other one I got over here in my truing stand already. So this one here, you can see some holes there, a correction hole over here where they screwed up, and that's probably pretty close to stock. Then once again you go on this side and someone's been in here dicking around with it and probably screwed it up. So what we got to do is find a weight that works close to see where it's at. This weight here is out of my flatted race bike, my KR, which is a pretty lightweight because it's made for a little lightweight 45-inch motor. It's a 98-inch heavy-ass motor. And if you notice, the weight is pretty close. If it's balanced, it won't move anywhere. This one's going to the bottom, so it's a little heavy still. And it should be straight up and down, not off to the side. So this one here is pretty close to the bottom where it belongs, so it's pretty close. The problem is the weight is really, really light. So not exactly what you should be running on a motor like this unless you run a really light balance factor. So that's this one. The more accurate weights are going to be these heavier ones over here. And see, these are heavier yet. So you can see how that one's a little bit thicker than that. It's also a bit bigger diameter. And this one over here, you can see how it's a lot lower height, a lot less lead, a lot less weight. So there you go. So I got weights for all kinds of stuff. So easy, this is the weight I use for normal Harley motors. Pan, shovel, Evo, doesn't make any difference. These one here, this is for an S&S motor. We got heavy rods in it. You use this weight. And then when you're using a real heavy motor with a high RPM all the time, especially above 5,000 RPM, you run this big bastard right here. It's a real heavy one. So this one's thick as yet. So S&S rods are heavy compared to Harley, so they're a lot heavier, and H-beam rods are heavy also. So when you run heavy rods and heavy pistons, you got to run more weight. All right, so this one here is pretty much a real light factor to it, but at least it's consistent. It's probably close to 50-50 balance factor, maybe a little less. It's a 50%. Hard to tell without actually measuring everything. But it's way light, so not what it should be. All right, I'm gonna take out this mandrel, swap it out. Alright, there's our new one. Now percentage of weights make a difference. A lot of people think 50-50 is what you use. There's a lot of people that use that. S&S always used to say 60% balance factor. They're lying through their teeth. They don't use that no more. They use more like 55, 56%. Doesn't matter what they say. Like I said, when you're racing, you run a higher yet percentage. 70% is what I like on my race bikes, but I'm spinning my bikes 5,000 RPM and up all the time, so they're different. So, like I said, this one's for my KR. It's a 7,000 RPM motor, pretty much always over 6. So that one I run at 70%. That's why it's got the really heavy weight compared to what it should be for. Alright, so this one here is basically a mess. So you can see how bad it is here. Yeah, hit on the camera there. There it goes. Okay, so just the same weight that we had in the other motor, or in the other flywheel. You know, theoretically they both should be the same. Yeah, you would think. Okay, that's the same weight as the other flywheel. So you can already see that it is way light. It's real heavy on the bottom. So you want to know how much it is, you go with 90 degrees and see how quickly it goes back. That's how far out it is. Quite a bit. Okay, so much for being consistent. Now we take the weight that should be in there, the big heavy one. Heat on the side down there. So, if we put that on the bottom, see how it comes up? So it doesn't want to be on the bottom. But it's exactly 90 degrees to it. Turn it 180 and see it's almost balanced there too. It's a little bit off, but at one point it will stay exactly in that spot. So this is the weight that they were using, except they're 90 degrees out. It's really heavy on the one side, so they didn't square it up correctly. So that means this bike's going to shake its teeth out because it's mismatched. You got this on one side, this one here, it's got the correct bob weight, but it's 90 degrees out of phase, so it shakes real bad side to side. So it's going to make a really shaky motor. Now if you use the regular weight in it for a stock type motor, you know, stock lighter rods and lighter pistons, that's this weight. You can see how the flywheel's heavy on the bottom again. I mean off that one side. But now you can see how this weight's light because it's balanced for a higher balance factor. So there you go. There's your differences. So the other flywheel is really light but balanced square. This one here has got the right bob weight, but it's way out of phase. So still got a problem. So what we're going to do is we're going to fix it. So I can use this weight here, which would be balanced for high RPM. That should put you close to 60% like S&S wanted. If I put this one in here, in there, this should be 60% on a light stock motor, but when you do the heavier rods and heavier pistons, it knocks the balance factor back a little bit. So this is probably going to balance around 55, 56%, which is kind of a trade-off for by balancing so vibration high and low. The motor's always going to vibrate from 3 to 3,300 RPM. It's just all the negatives on a Harley motor come in at that point. So when it's out of balance, it's out of balance, and there's no way of stopping it. If you change the bob weight, you can make it shake below or above that number quite a bit or a little. So back in the 30s and 40s, Harley balanced their motors for idle, so they're really nice at idle. As you rev them up, the bars went from being like this to like this. They got huge because they're shaking so bad. On a race bike, we don't care about idle, so at idle it bounces a lot. The front wheel's bouncing off the ground almost from the shaking so much. You rev it up, take up 6,000, 7,000 RPM, it goes dead smooth. That's where I balance my stuff for. Street bike, you go something in between. So this customer here, he wants to be more of a street than race. So we're going to build a torque motor, not a high RPM motor. So we're going to go ahead and put the the stock one in there. Not that one. Damn it, what did I do with it? This one. So this will bring this should put us around 55-56%, which is what I usually use for trading off someone they want smooth and high RPM mix. So there you go. That's our differences. So now we got to fix this one and then fix the other one. Now we can either fill all these holes up or just drill new holes. When you drill more holes, they get lighter. These are already light in flywheels compared to Harley. If I lighten these up even more, it'll be more like an Evo bike. Evos have real light flywheels. So I'm just going to go ahead and drill this because it's not worth the effort and time to make a bunch of plugs and fill this all in to make the wheels a little bit heavier, because that's all we're going to do. We're going to balance it correctly when we're done, so it doesn't matter. But this one here, it's not worth the hassle. So what I like to do is I like to chamfer these holes so there's no sharp edges here as best I can. And we'll do that. Now this is the right side flywheel, because there's no timing marks up in here, and you can also see there's an old hole in here, so that tells you it's the pressure side. So it doesn't really matter about all this. Now if this was the left side, we had timing marks over here, there'd be marks right in this area right here. That's where your timing mark is for your front cylinder. So actually front cylinder would be over here. This is where the rear cylinder mark would be, is over in this area. But anyway, you don't want to be drilling all through here because that's where your timing marks belong. I don't like drilling on this side anyway. Usually they're on this side, it's had dynamic balance, so they spin balance it. I static balance, static we do on this side. Alright, so I'm going to chamfer these holes out, and then we're going to find a drill bit that's about, usually I don't go this big of a drill bit either because it's real thin. So I'm going to find a drill bit I'm going to use. I used to have one set up for using all the time, but that was in the old shop. We're in a new shop now. We'll have to find a new drill bit. Alright, so we're going to go over here and see what we're going to do here. Usually I use something around 7/16 as I recall. So let's see what we got laying around here in a drill bit that's close to a 7/16. We got a bunch of drill bits just laying out near the drill press. The problem is our drill press is not here anymore. We're using that drill press, so it's different. Alright, so that could be about the right size. So I'm not going to concentrate on the bad side. We're going to go over here to the good side. And you can see how these holes are smaller. More like that one. This one's a little bit on the small side, so we want to use that one. So let's go see what they used. There's a 7/16. Oh, what a shocker. That's the number. Okay, so that's going to be the number I'm going to use, I think. Let's go check the other flywheel and make sure the stock hole is the same size. We just happen to have two holes in here that are stock. There you go. It's good. Alright, so 7/16 is going to be our number. So we're going to use this drill here. So we'll put that over here to use. Next thing I could do, I got a counter bore or counter deburr the surface. So I take a round burr, you go in there like that, round burr. Alright, so we're going to go ahead and set our mill up here. Yeah, mill used to be easy before to use, but it's not as easy anymore. Turn it on and deal with it. I think now we'll just go over here and do a drilling press table. Stuff on the floor. Alright, one advantage of this shop is we can actually put a camera over here to get a better view of the drill press. So, make sure it's fully down. Back a little bit so you can see better. Alright, you should be able to see what I'm doing pretty easy now. I'm going to have to change the speeds up here on top to change my gear. So when you do a bigger drill, we go up higher, which makes it go slower. So this is a smaller drill press, not as heavy duty, so you gotta turn your speeds down a little bit. Alright. First thing we do is deburr. low gear. Chamfer the holes. Alright, so those are all chamfered, deburred. So much I can do with these holes. Alright, still pretty sharp, but that's going to have to work. Alright. Good spot to work. All right. Yeah, could go on this side over here. We got to press our weight in here. So we got to get some, use our press. Take your flywheel, put it right there, find our weight. Right here, we're using the 5,000 RPM one. I have a mark on my weight, so I know exactly where it is every time. And I also mark my shaft, so I know where it's at. So 10 years from now, I come back here, put this back in, it should repeat pretty damn close. If your tools aren't repeating, it's not very accurate. The way I do stuff, it repeats fairly well. Okay, I don't need a lot of pressure on this, just light pressure is all it takes. That's enough. Just enough to push it in there. Make sure it's tight so it won't fall out. And we're good. There. You can see I got my mark right here into my shaft, and the weight's up there. So I know exactly where I'm at. Okay, now I go over here and check our balance. See where we're at over here. So you got a couple different ways to do balancing. Static and dynamic. This is static. Dynamic means it spins when you check it. Okay, this one has two counter rotational wheels here. See how they're moving back and forth right now? So these have ball bearings on the inside here, real low drag. And this gives you a very low drag situation. The other way of doing it is you can put on a balance beam. This here's a balance beam. You have two round rods, and you have this sitting on top of that, going back and forth, and it will roll back and forth. As long as you level these out so they're all level, you can have that laying on top of this like that. If you have a flat thing like this, like an old lathe laying around, you can use an old lathe. You can just have it going across your surface here. Once again, you got to level the lathe out, because if it's not level, it's going to make this roll downhill. So you can see how low drag this is. It keeps going back and forth, back and forth. Put a little drag on it, slows it down. Then you just balance it like this a little bit to shake it up, and it'll let you know where you need to drill. So I don't want to drill right there, and obviously I don't want to drill up here. I don't want to put holes all the way through my flywheel. So this is a no-no area, and usually that's where I drill. But in this case, it's real light up there anyway, so we ain't gonna be drilling over there. So these I will never hit, but I'm not a big fan of putting drills right here if I don't have to. So it looks like that hole right down there's already in there. Looks like it's dead center. Can't see up in there to see, but yeah, it looks pretty close. It looks like it's pretty close to right on dead down. Alright, so if I concentrate just drilling next to that hole and around it, it'll be close. And I need to drill out how much weight we need to take out. You go 90 degrees, and that's how much weight you got to take out. Now you have to know what that is, but what that is going to be a couple of big holes. That's what it's going to be. There'll be a couple of these holes like this. Okay, so we're going to be drilling all through this area here. So I'm going to put 2 holes next to this one, and I'll drill all 3 down because I don't want to go deep with 1 hole. I don't like having 1 hole like that really deep. I'd rather have 3 holes that are close. They only go like that deep. You know, keeps the flywheel stronger. Okay, so we know what we're going to do. I'm going to make sure we don't drill this one. We're going to drill that one down there. So it's the one on the right side, not the left one. Okay, if you drill on the wrong one, you have a problem. I've done that before. That's when you have to go back and put correction holes in there. And it's very visible when you do it. It's like the flywheel at Harley has correction holes in it already. Alright. So the hole we're going to be drilling is just one that's already real deep. So we're going to add a couple more holes next to it. We need more speed for this to work efficiently. Make sure that doesn't roll away. Okay. There we go. A little slow, but be alright. Cut very well. I don't have enough horsepower either. You hear it squeaking, it ain't happy. Alright, so let's go see what's wrong with this drill, because obviously it sucks. Alright. Looks like it should be cutting alright, but it's not. This drill's been sharpened, but it's not the best. So you can see this corner right here is all rounded over. This one here is used a little bit too, but not too bad, but it's rounded also. It looks like they're cutting fairly even, so I'm not sure why it's squeaking so bad. It's obviously rubbing on the back side here. It's rubbing down in here, but there's enough angle here it should not be rubbing, so I'm not sure why it's rubbing there. Shouldn't be rubbing down there. Alright, so I'm going to go resharpen this and see what I can do.